Let's talk about perpendicular bisectors and angle bisectors. So we're going to start out with some theorems. So the first one says, if a point is on the perpendicular bisector of a segment. So first let's talk about what a perpendicular bisector is. So a perpendicular bisector has two pieces. The first part says it's perpendicular. So that means that it's a segment that is, or a line, a point, something. It has to be at least a line. And it's going to be perpendicular to the segment that we're talking about. So it's perpendicular to this segment that we're talking about, and it's also a bisector, so that means that the two pieces are equal. So a perpendicular bisector bisects it at the midpoint, or it's perpendicular at the midpoint. So we know that it's equidistant, the intersection point is equidistant from each point of the segment, but it's also equidistant from the endpoints. So we know that this point up here is going to be the same distance from this endpoint of the line segment to this endpoint of the line segment. So the converse of that is if the point is equidistant from the endpoints of the segment, so we got a nice little triangle here, then the point is on the perpendicular bisector. So we can use this either way. We can say if it's on the perpendicular bisector, then it's equidistant from the endpoints, or we can say if it's equidistant from the endpoints, then it's perpendicular bisector. So now let's look at our angle bisector theorem. If a point is on the bisector of an angle, so it is on the bisector of the angle because the two pieces of the angle are congruent that it forms. So if that's true, then it is equidistant from the rays, or the sides of the angle. So the sides of the angle are called rays. So the converse, if it is equidistant from the sides, then the point is on the angle bisector. So now let's put some of these into action. All right, so we have two examples here. In the first one, our first task is to name all of the congruent segments. So I've got these marked. That's the first thing I noticed, is that these two have these little dash marks. So those two segments are congruent. Let's say CQ is congruent to QD. That's by the markings. So we know those two. Next thing that jumps out is that these two segments are both measured 7, so that means that those are congruent because they have the same measure. So TC is congruent to TD. So now we're going to have to use our brain a little bit. So that first theorem that we talked about was the perpendicular bisector theorem. And I noticed that this is perpendicular. Also that these two segments are congruent. So that means that this is the perpendicular bisector. So any point on this bisector is equidistant from the endpoints C and D because that is the segment that was bisected. So if we look, notice that P is on that perpendicular bisector. So if a point is on the perpendicular bisector, then it is equidistant from the endpoints. So that means that CP is going to be congruent to PD. So that's the one from our theorem. So CQ is congruent to QD by the markings. TC is congruent to TD by the definition of congruence. And CP is congruent to PD by the perpendicular bisector theorem. So is T on the perpendicular bisector of CD? So if we extended this line, would T be on it? So what we have is that TC is 7 and TD is 7. So since those two segments are congruent to each other, they're the same measure, that means that point T is on the bisector. And that is by theorem 6.6, the perpendicular bisector converse. So for this one, we got this from the perpendicular bisector theorem. The perpendicular bisector converse proves that a point is on the line. All right, so in example 2, we've got this figure. It's made up of many triangles. And we're going to try to figure out these lengths that it's asking for. So the first one it asks for is SW. And whenever I look at SW, I notice that it's got markings that SU and UW are congruent. So since this one measures 4, that means that this angle, or this side, also measures 4. So if I want the whole line segment SW, I'm going to do 4 plus 4, and that will give me 8. The next thing we want is UV. So I want UV, and what I notice is that point V comes off of this ray right here. And this ray is bisecting the angle W. So since this is an angle bisector, the angle bisector theorem said that if a point is on the angle bisector, then it is equidistant from the sides of the angle, or the rays. And so since this one is 3.4, that means that this one will also be 3.4. So UV is 3.4. Next thing is the measure of angle XTV. So XTV. This is bringing back our right triangle corollary for the triangle sum theorem. It says that these two angles are going to add up to 90. So for angle XTV, I'm going to say 30 plus T equals 90. So if I subtract 30 from both sides, that means that T is going to be 60 degrees. So the measure of angle XTV is 60 degrees. So now we have VWX. VWX. All right, so I know that it's congruent. Whatever this angle is also going to be this angle. I don't have enough information in here to figure out what the angle is, but I do have enough over here. So if I can figure out what this angle is, I can because of the right triangle corollary. This is a right angle, so this will be 50 plus whatever this angle is, have to add up to 90. So whenever I subtract 50 from both sides, I get that this angle is 40 degrees. So if this side's 40, then this side is 40 as well. And the last one I have to find is USB. All right, so let's look at what we know. So I know that this triangle has an angle of 40 up here and 40 up here. And USV is an angle in the biggest triangle. So if I look at the biggest triangle, I notice that I have those angles. I have 40 and 40 for this top angle, which means that the whole thing is 80. I have that this corner T is 60. And all triangles, even though it's made up of many smaller triangles, all triangles add up to 180. So if I know that this angle T is 60 and W is 80, I can find angle S by using that angle sum theorem. So I'm going to say 80 plus 60 plus S equals 180. Then I will subtract 140 from both sides so that it cancels out both of these. And that leaves me with S equals 40. So this angle has to be 40 degrees in order to complete this triangle. So it doesn't matter that we don't know the other angles of this triangle. We could figure those out if we need them. But we are able to find it because of all of the triangles adding to 180.